From the previous lesson, we found that the row and column space of a particular matrix A, which has been reduced to a row echelon form, so can be determined by the leading one here. So we have the leading one in the first row, leading one in the second row, and leading one in the third row. So this R1, the first row, R2, second row, and the third row, R3, are the bases for the row space. And coincidentally, the corresponding column is the basis for the column space. So we have the C1 prime here, C3 prime, and C5 prime. And we know that the column space, the bases C1 prime, C3 prime, and C5 prime here are the basis for the column space of R, matrix R. In order to find the basis for the original matrix A, we have to refer back to the original matrix. So we take the same position, which is the first column, third column, and the fifth column, and we have the C1, C3, C5. So these three are the bases for the column space of original matrix A. For both matrix A and R, they have the same row space. Now we see that the row and column space of a matrix A, the row space and the column space of a matrix A have the same dimensions, because there you decide it based on the leading one. So if you have three leading one, which means that you have three bases for the row space, and similarly you will have three columns bases for the column space. So the dimensions of a row space is equivalent to the dimension of a row space of R for the original matrix A and the reduced form, and the dimensions of the column space of A is the same as the dimension of the column space of R. By the way, if you have forgotten what is the meaning of dimension, the dimension is the number of bases. So since both row and column spaces depend on the leading ones and they have the same dimensions, so the common dimensions of the row space and column space is called the rank. We have a specific name for it. So the rank of A is represented by the dimensions of the row space or the column space, and is denoted as the rank of A, and the dimensions of the null space of A. So this is the nullity of A and is denoted by the nullity of A. So let's look at one of the example here. So find the rank and nullity of the matrix A. So you have a original matrix A. In order to find the rank and the nullity, the first step that you need to do is reduce it to the reduced or row echelon form, because we want to identify the leading one here. So apparently we have two leading one in the first and the second rows. So if I'm going to write it in the AX equals to 0, because we need to find out the nullity. So nullity is for the homogeneous linear system where AX equals to 0. So the first equation, you're going to write it in this way: x1 for the first column, 0 for the second column, so we don't have a x2 here. So -4 for the x3 and so on equals to 0, and the second row do the same steps. And then we know that the first column and the second column are the pivot column. So the third, fourth, fifth, and the sixth columns, we do not have a leading one here. So which means that there are the unknowns, or known as the free variables. So you could elaborate as any terms for the x3 and this x6. So you can have a x6 equal to, let's assume x6 equals to u, x5 is t, x4 is s, and x3 is r. So we can express the x1 and x2 in the form of x3 until x6. So in this case, we use the alphabet R, S, T, U to represent it. It's easier for us to write it this way. Then the solution for x1, x3, x4, x6. So this is the vector, the new vector for our solutions, where you are going to plug in every expressions here. So x1 depends on the R, S, T, and U, and x2 depends on the R, S, T, and U, whereas x3 is solely depends on R, x4 for S, and x5 for T, and x6 for U. And that's why when you write it in this vector form and you factorize out the R, S, T, and U, you have the four vectors here. So these four vectors form the basis for the solution space of AX equals to 0. And the nullity of A is the dimensions of the null space, or known as the number of bases for the null space of these solutions. So we have 4 bases here, so the nullity is 4. And how about the rank? So since we only have 2 leading one here, then the rank will be 2, because the rank depends on the dimensions of the row space and column space. So we have 2 leading one here, so the rank will be 2. So this is how you decide on the rank and nullity of a particular matrix. And here is a statement or a problem for you to ponder. If a matrix is not squared 2 by 3 or 4 by 2, so what is the maximum possible rank for it? So remember, the rank depends on the leading one. So try to ponder about this. The dimension theorem for matrices states that if A is a matrix with n columns, then the rank of A plus the nullity of A is n. So in another words, it means that the rank is the number of leading variables, whereas the nullity is the number of free variables, and the n is the number of unknowns. So the number of leading variables plus the number of free variables would give you the same number of unknowns. So let's consider the same examples which we have discussed previously, so the A and the reduced matrix form. So from this case, we know that the rank is 2 because we have 2 leading one here, and the nullity, which we already shown here we have 4 bases here, so it's 4. So when you sum them out, you have 6, equivalent to the first unknown, second, third, fourth, fifth, and sixth unknowns. Now try to find the number of parameters in the general solution of AX equals to 0 if A is a 5 by 7 matrix of a rank 3. So 5 by 7, you know that we have 1, 2, 3, 4, 5. You have 5 rows and you have 1, 2, 3, 4, 5, 6, 7 columns. And you have a rank 3, which means that you have a leading one, leading one, leading one. So 3 rows contains the leading one. And how about the nullity? So we know that we have 3 leading ones here, which means that we have 3 pivot columns. And the other 4 columns will be the free variables, and that's why the nullity is the number of unknowns minus the rank, which is the 4 parameters. So this is actually related to the degree of freedom, where the degree of freedom was derived from these definitions. So let's imagine that m is the number of rows or the number of equations, and n is the number of columns. If your number of independent rows or number of independent equations is more than the number of unknowns, so it is an overdetermined case. You have too much of equations or information, so most probably your solution will be inconsistent. And if your number of equations is lesser than the number of unknowns, so it could be an underdetermined case, so we lack of information, so either it is inconsistent or it has infinitely many solutions. And what would be the case if the number of equations, independent equations, is equals to the number of unknowns? Well, try to ponder that. And lastly, the fundamental spaces of a matrix. So matrix A n is transpose A transpose. So the row space of A, when you transpose the matrix, so let's say you have a 2 by 3. So this is the matrix A. And when you transpose it, the column will become the row, and the row will become column. So this is the A transpose. Apparently the row space of A, so we have 2 here, is equivalent to the column space of A transpose, because the row space, the row of the original matrix A already transposed the column in matrix A transpose. And similarly for the column space of A is the same as the row space of A transpose. And the null space of A and the null space of A transpose are not necessarily the similar one. So we can sum it up, summarize it into 4 fundamental spaces of matrix here, which is the row space of A, column space of A, null space of A, and A transpose. And from this definition, we know that the rank of A is the rank of A transpose. The rank of A plus the nullity of A transpose is the number of equations. So Y. try to ponder this based on the statements that we discussed here. And the dimensions of row space of A is the R, and the dimensions of null space of A is equivalent to n minus R, where n is the number of unknowns and R in this case is the number of leading one.